I would like to present the result of our work regarding information system for direction finding of signal source in ultra low range. Low frequency signals generated by natural and anthropogenic sources propagate through the Earth's ionosphere waveguide over distances of several thousand kilometers. These signals can be recorded for locating thunderstorms, fronts, conducting atmospheric and ionospheric researches, analyzing space weather, and even predicting earthquakes. VLF anomaly indicates a shift in the electromagnetic vector over surface conductive materials, and hence can be used in order to find natural ores. Nowadays, military applications of such methods are quite important, and these include monitoring of the above-ground detonation of nuclear weapons. For location of the signal source, there are two main methods that are used. One is trilateration and another is triangulation. Trilateration implies using of at least 3 synchronized detection stations, measuring subtle differences in time of arrival and of the signal and solving the equation for unknown coordinates. On the contrary, triangulation implies measuring bearings of the received signals by at least 2 stations and finding signal source at bearing intersection points. And each of these 2 methods have its advantages and disadvantages. For example, trilateration is more accurate when station timing is well synchronized. It works very well for dense networks if you have lots of receiving stations. It is insensitive to angular uncertainties of bearing finding. Nevertheless, it requires precise time synchronization between all receiving stations. It is a nanosecond level for best accuracy. Needs at least 3 stations for 2-dimensional locations and even more for 3-dimensional location, and is susceptible for errors due ionospheric dispersions, especially if we are talking about long range location. Such approach is used by large networks, for example, such as Blitzortung.org. It's an open source network for lightning detection. On contrary, triangulation has its own advantages and disadvantages. It can work with only 2 stations. It have lower dependence on exact timings and hence ionospheric dispersions, suitable when using direction finding. Antennas work well even with long range, low frequency signals. But on contrary, it is sensitive to bearing errors. Small angle errors can cause large location accuracies, and accuracy finally degrades with increasing distance from the station baseline, so-called geometric delusion of precision. And the main disadvantage is that such approach requires precise knowledge of antenna orientation and calibration. So our task was to modernize the Soviet Ka-120R station, and you can see its state on this illustration. Finally, we chose to use only antennas from this station and develop modern system. This system comprises of 4 antennas from the old system, 2 loop antennas directed north-east and north-south and east-west, north, south and east-west direction, 1 omnidirectional whip antenna, and also wideband antenna for determination of signal type. Okay, so we have 3 antennas with their radiation patterns directed in east-west direction, north-south direction, and hence it is not possible to define from which side of antenna signal was received. We have to use additional omnidirectional whip antenna in order to distinguish this direction. So finally, BRIN can be found as a arctangent of the ratio of the signal levels of two loop antennas, and obviously we have to correct it for side uncertainty by the relative phase difference of a loop and whip signal. This algorithm was implemented in PC software. That piece of software is able to register raw signals and also is able to find impulses from distant lightning storms and find bearing of or direction from which this signal is originated. It also plots a diagram of azimuth versus relative distance to that, or pseudo distance to that signal, just for visualization. Obviously, the one station is not able to find true distance to the signal source. So this information, this bearing, together with precise timing, is transferred to the server, where it is stored in the database for further processing. This processing is finding at this intersection point of 2 bearings taken into consideration as a globe shape. So we should solve the geodesic intersection point problem. Geodesic in our context is a curve representing the locally shortest path between 2 points on the surface. And to do that, we chose to use geographic leap. It's a C++ library that works well with WGS84 representation of reference ellipsoid of the S globe, of the S globe. And this library helps us directly find the intersection of two geodesics. So after we found this intersection, we can point this source on the map, and the end user is able to see all these sources, and also system is capable of classification of signals, whether they are of natural origin, in other words, lightning, or of artificial or anthropogenic origin. So as a conclusion, I could say that we modernized K120R hardware software system, and during that process we enhanced sensitivity and functionality of that system, and our specialized software supports multi-station signal processing, automatic recognition of no signal types, user interaction, data protection, and real-time signal transmission and visualization. Further, we want to improve our algorithm of source type recognition and also want to improve our capabilities of ionospheric condition analysis. Thank you for your attention.